Hello, my name is Andres, and I present our paper on learning symbolic planning representations that are grounded. So to set the stage, the aim of the paper is to learn PDL-style action models from a sample of state transitions. This has been done before, but a distinctive feature of our work is that states are represented as parsed images. So what is a parsed image? It is a description of what goes on in the image in terms of the objects present in it, the types or classes of these objects, as well as a small and fixed number of visual predicates that encode spatial adjacency, relative size, and things of that nature. And these are descriptions that could be generated from the output of a vision module. The domain dynamics that we learn, which are in a PDDL style, are however not always definable in terms of these visual predicates, or aren't simplest if defined with them. So in fact, the learned representations that we get use higher level predicates that are derived from these visual primitive predicates. And we call these higher level predicates grounded predicates. The method that we use builds on previous work for learning these type of models from the structure of state graphs without state information. So on top here, you have a depiction of the visual predicates we use in the language for spatial adjacency, relative size, and shape of objects. And below you have images for a block world state and a circumvent state, together with the corresponding parsed image descriptions. You can see that these descriptions contain constants for the objects that appear in the image, their type declarations, and some relational information. As I said, the models that are learned typically don't use these visual predicates, but instead they use derived predicates, which correspond to logical conditions that are definable with these visual predicates. So for example, the typical notion of a block being clear in blocks world is definable here by the condition there is no other block such that the block is below it. So these are the type of predicates that the learner may select to use in the action models. And here's the formulation of the learning task. So what we're given for learning is, first of all, a sample of transitions, each of which consists of an O to D state, the label for an action that is performed, and a successor state S prime. And the action label alpha does not include the action arguments, only the type of action that's being performed. So this is the data that we have to learn from. And then we also have a set of ground predicates, which are the ones that can be chosen to appear in the learned action models. These are derived predicates such as clear in blocks world. From this input, we want to learn two things. First of all, we want to learn the action models, which are going to be in lifted strips representation, and they will feature some predicates P1, P2, etc. And secondly, we want a function sigma, which is the grounding function that will map each of these predicates in the planning domain to a grounded predicate from this pool P here. So it's going to indicate that P3, for instance, corresponds to clear in blocks world. Now, sigma and D induce a map, which we denote by edge, from the O to D states, the ones that are in parsed image representation, into planning states. If we know the O to D state, we can compute the corresponding planning state by evaluating the derived predicates. And this mapping from O to D states into planning states has to satisfy two properties. The first one is that if the O to D states are different, then the corresponding planning states must be different as well. And the second one is essentially an isomorphism condition. So it says that for any state S and any action label alpha, the following two multisets must be equal. So the first one we get by considering the state S and every instantiation A of the action label alpha, looking at the possible successors of S by any of these actions, and then computing the corresponding planning states. And this collection of planning states must be the same that we would get if instead we first considered the planning state that corresponds to S, computed all its successors in the learned domain, not in the original domain, and collected them. So if these two multisets are the same, then we consider the learned domain correct. The way we solve this learning task is by casting it as a combinatorial optimization problem. And it only contains two hyperparameters, the maximum variety of actions and the maximum number of predicates. And the optimization criteria are things such as selecting the smallest RET fractions. And this problem is then expressed and solved by an answer set program, specifically using the Klingo solver. And to wrap up the presentation, here's a quick summary of the experimental results. These are some planning domains that we considered and tested the solver against. The solver was run in an incremental way, and this is the number of iterations for each domain that the solver went through before finding a correct solution. We call a correct solution one that passes a certain verification, which involves testing that the action models that have been learned correctly predict state transitions for a number of unseen instances. And these are the number of instances and states that were used to learn these correct models, as well as the time that was required to solve the programs, to ground the ASP programs, to perform this verification and in total. Thank you.